Welcome to This Explainer. Today we're tracking a totally invisible protagonist. We're going to follow a simple, unseen breath of air as it embarks on this wild, sky-dominating journey, transforming from absolute nothingness into one of the most powerful forces on Earth. All right, let's dive right into this.
I want you to pose this question to yourself for a second. We look up at clouds every single day, right? And we usually just dismiss them as these weightless, wispy balls of cotton floating by. But the reality is actually staggering. A single, ordinary summer cumulus cloud, the kind you see on a perfectly pleasant afternoon, can hold up to 50 tons of water. To put that into perspective, that is the weight of about 10 fully grown elephants just suspended over your head. So how exactly does an invisible pocket of gas become a 50-ton monster? To really get how this happens, we've got to introduce the main character of our story, the air parcel. You see, in thermodynamic physics, we can't look at the entire atmosphere all at once. It's just too big. Instead, we isolate this small, discrete pocket of air, maybe just a few meters across, which has a consistent temperature, pressure, and density. By watching how this one specific air parcel reacts to the heat of the Earth, we can unlock the whole secret of cloud formation.
Which brings us to part one. The spark of warm air.
Every great storm, literally every massive cloud system you've ever seen, actually starts on a bright, sunny, fair-weather day, and it needs two vital ingredients. First, we need the spontaneous uplift of heated air. As the sun just beats down on the Earth, our little air parcel warms up, it becomes less dense than the air around it, and it naturally begins to rise like a hot air balloon. But warm air isn't enough on its own. The second ingredient is microscopic impurities floating around in the atmosphere. Things like sea salt, dust from deserts, or even smoke. We call these condensation nuclei. Without these little specks of dirt, our cloud can never actually take physical shape.
Moving on to part two, birth of a cloud.
So, the crucial point here is the physics of the ascent. As our warm air parcel rises higher and higher into the troposphere, the pressure around it drops. This causes it to expand or decompress. Now, this decompression means the air molecules aren't colliding as often, which causes the temperature to drop. We call this adiabatic cooling. Actually, if the air is dry, our parcel cools at a highly predictable rate, exactly 10 degrees Celsius for every kilometer it rises. Eventually, it cools down so much that it hits its saturation point, known as the dew point. The air simply cannot hold its invisible water vapor anymore.
And boom, this is the exact moment of birth. Remember those microscopic impurities we just talked about? Well, the water vapor suddenly needs something to cling to, so it wraps around those tiny condensation nuclei. And when I say tiny, I mean it. These particles are often just 0.1 millionths of a meter wide. Millions and millions of these droplets gather together, and suddenly a fluffy, cotton-like cumulus cloud just bursts into existence. Notice the perfectly flat base on those cumulus clouds? That horizontal line isn't an accident. It is the exact altitude where a rising air parcel reached its dew point and condensation began.
All right, part three, growing through unstable skies.
Now our cloud is fighting to rise. If the atmosphere above it is stable, the cloud just kind of flattens out and dies. But if we have what's called atmospheric instability, things get crazy. This means the environmental air around our parcel is exceptionally cold. Because our rising air parcel is still warmer and less dense than the surrounding freezing air, it becomes incredibly buoyant. It doesn't just drift, it is violently pushed ever upward, rising spontaneously through the troposphere.
And here is where the physics get truly fascinating. How on earth does the cloud stay warmer than the freezing upper atmosphere? Well, it uses a secret fuel, latent heat. When water vapor changes its phase into liquid droplets to form the cloud, that physical phase change actually releases heat right into the air parcel. This latent heat actively retards the cooling process. It acts as this massive internal energy source that keeps our cloud warmer, less dense, and constantly rocketing upward.
You can often spot this instability right in the sky. When you see formations like these altocumulus clouds, they're basically a giant warning sign for elevated instability. Our original friendly little cumulus cloud is evolving. Fed by that latent heat and the unstable air, it transforms into a species called cumulus congestus, a towering cloud that is suddenly growing way taller than it is wide.
Which takes us right into part four, the mighty cumulonimbus.
Let's do a quick vocabulary check. The word nimbus is Latin for rain-bearing. Whenever meteorologists add that as a prefix or suffix to a cloud name, it means precipitation is happening. So our towering cumulus cloud has grown so immense, it is now officially a cumulonimbus. It is capable of massive vertical development, often punching right up to the stratosphere, and it brings with it lightning, thunder, and heavy, heavy rain.
Now let's really take a minute to unpack the anatomy of a supercell, which is the most dangerous type of cumulonimbus. Inside this towering beast, extreme chaos is occurring. If you have strong wind shear, meaning winds are blowing at different speeds and directions at different altitudes, it actually tilts the whole storm. This tilting is a big deal because it prevents the falling rain from killing the rising warm air. The entire structure can even begin to rotate, creating what we call a mesocyclone, which you can see spiraling right in the center. High up in the freezing overshooting top, ice crystals and supercooled water droplets are violently colliding, swapping electrical charges to create lightning and clumping together to form hail. It's a highly organized, terrifyingly efficient atmospheric engine.
At the mature stage, this cumulonimbus is defined by a violent internal battle. On one side, you have the updrafts, this continuous, powerful flow of warm, moist air feeding the storm and releasing latent heat. On the other side, you have the downdrafts. As millions of water droplets and ice crystals finally become just too heavy to be supported by the updraft, they plummet to the earth, dragging freezing cold, dense air right down with them. These downdrafts can hit the ground and spread out at speeds of over 160 kilometers per hour.
So how does it end? Part 5. The storm's final act.
What you should really take away from this timeline is the shockingly fast, violent lifespan of a typical air mass thunderstorm. It takes massive amounts of energy to create these systems, but they burn fast. From the moment our air parcel condenses into the cumulus stage, to the mature, lightning-producing stage, and finally to its death in the dissipating stage, the entire cycle often takes less than an hour. Sometimes the whole shebang is over in just 30 minutes.
The wild part is, the mechanics of the cloud's death are built right into its creation. We call it the chokehold. Remember that internal battle we talked about? Eventually, the falling precipitation and the massive downdrafts become so widespread that they literally overtake the updrafts. The cold, falling air chokes off the supply of warm, moist surface air that the storm desperately needs to survive. Without its fuel, the towering structure just collapses under its own weight, leaving behind only light rain and decaying, wispy clouds.
So why does all this happen? What is the overarching purpose of this violent, beautiful life cycle? Well, it comes down to balancing the Earth's heat budget. Our planet receives massive amounts of solar radiation at the surface. If that heat just stayed down here, the surface would be completely unlivable. These 50-ton monsters are actually Earth's vital cooling mechanisms. They take that excess surface heat, convert it into latent energy, transport it thousands of meters into the upper troposphere, and release it. In doing so, they balance the daily heating cycle and drive the global hydrologic cycle, distributing life-giving water all across the continents.
It completely reframes our view of the sky, doesn't it? The entire process is just a thermodynamic masterpiece. So, the next time you look up and spot a fair-weather cloud drifting by, ask yourself, are you just seeing a fluffy wisp of water vapor, or are you watching a 50-ton monster, quietly breathing in the heat of the Earth, just waiting to exhale? Keep your eyes on the skies, and thanks for joining this explainer.